Good morning to everyone. My name is Adrian. I like to come up with convoluted presentation titles that are hard to follow. So I will be talking about how you can emulate Linux malware, like Sabina said, and this is my approach using something called the Unicorn Emulator Framework. If any of that is unknown to you, I'll try to explain as we go along, so I hope you'll enjoy the presentation. Like I said, I'm a security researcher. I work with Ixia's application and threat intelligence team. I work with sandboxing, phishing, look on the newest and coolest exploits, try to track them in our honeypots and stuff like that. And a lot of the work that we do relies on automating stuff. So this POC that I'll try to explain about is something that's aiming to automate as much of the malware analysis work that we do, up until one point. You can follow me on Twitter. We also have a blog that I sometimes blog on. And I'll try to keep the content short. Since this is a short presentation, I'll just come up with the how, the why, and show you some examples of how things work when trying to do this. So, if you're unfamiliar with malware packing, basically the idea is to wrap your malware that might get detected by antivirus products inside some sort of shady box. So you'd have the original malware binary. It's wrapped inside a separate executable that is going to unpack it, uncompress it, unencrypt it, and then execute it. And this all happens on runtime. When you execute the new binary, it's going to unpack the contents in memory and then execute the original. So you might be asking why someone would do that, since it just looks like adding complexity. Well, the reason is antivirus products and security products in general rely on signatures. They do different types of analysis, and one of these types is called static analysis. For example, looking for interesting strings inside a binary, looking for important functions, looking for anything that can be analyzed without executing the binary itself. In this case, this is a DDoS bot that I also showed last year, and these are some of its commands that you can see in clear text just by analyzing the binary, just by looking at it. When you pack the malware, you just get random strings. You can't find the original anymore, so that way you lose an indicator for the antivirus or anything to be able to detect. So there are many ways of doing packing. You can find off-the-shelf packers. You can find open source stuff. The common de facto tool right now with the Linux malware seems to be UPX. UPX is an open source tool. It has a nice decompression option that, but with some work, can easily be bypassed, hindering analysis. There are other off-the-shelf tools, open source, commercial, like VM Protect. We have unpacking tools for some. We have unpacking strategies for others. And you also have custom packers. Someone writing their own packer from scratch. Someone modifying an open source tool such as UPX. And unpacking these generally requires some sort of manual labor if you want to simply unpack without executing the binary, and you need someone who's pretty good at using a debugger, knows some knowledge of assembly, knows something of the internals of how binaries generally work. So like I said, I try to automate stuff, and I was looking into how you can automate this. The simplest and most direct way to do that is to use a sandbox. That means executing the malware or the malware candidate, suspicious sample, inside the virtual machine. Generally, you use a virtual machine that you have a clean state for. You would restore it to a clean state. You would execute the malware. The machine is highly monitored, and you can see what happens during execution. And this is pretty hard to customize, because you have to add more monitoring tools as things go about. The tools themselves might get detected by the malicious author on execution, and the malware stops running. And this is pretty expensive. You sometimes have to wait for a couple of minutes until everything goes. You also have trouble scaling, because I need to add one more package to my virtual machine, then I need to deploy a VM template on a lot of sandbox boxes. So that easily becomes hard to customize. Emulators have been used for some time. The go-to tool so far is kimoon, which is a nice emulator, but it has the same limitation of being pretty hard to customize. It's written in C code. You have to do some recompiling. You have to do a lot of pretty hard labor to be able to customize it. And someone also suggested we could overload the Linux system call table. I'll explain what system calls are if you're unfamiliar. Basically, just overloading some default services that Linux would provide, and then tracking and seeing what happens. And this is about as hard to customize as anything, since it requires recompiling, modifying kernel modules, reloading kernel modules, and stuff like that. So again, seemed hard. I don't want to take this approach. So on to Unicorn. You can see a unicorn over there. What's Unicorn? At some point, some people started working on 3 frameworks called Capstone, Keystone, and Unicorn. They're used for assembly, disassembly of binary code, and Unicorn is an emulator. That means it's able to take CPU instructions and execute them as would happen on a real-life CPU. So that's the starting point for this. We have something that's able to execute CPU instructions in a binary. And at first, it seemed kind of easy. What do you have to do to execute a binary? You just take it, load it into memory, then execute. Nice and easy. Should actually become easier as time goes by. The reality of any research trip is something like this, unfortunately, but it's also fun. So the reason for that is that things get a bit more complicated. The operating system, when executing a binary, does a lot more work behind the scenes than we are aware of. Basically, it loads it into RAM. It would allocate CPU time, which we don't have to worry about when doing emulation. The CPU would execute instructions, and that's the part that Unicorn does for us. It's able to do all of that. And then the application is going from time to time to ask for different services from the operating system, like asking for more memory, asking for writing to a file, reading from a file, and stuff like that. So the middle part, Unicorn helps us with, but parts 1 and 3, the ones on the left and right, we have to do them on our own. So how would you load a binary into memory? Oh, if you start searching online, you find some information about how Linux ELF binaries are loaded. You find that they have some mappings. This is an example of a mapping the file contents to memory. For example, this part here says that you should go to the beginning of the file, grab so many bytes, and then load them into memory, maybe at a specific address, allocating as many bytes for it. You can also have different types of mapping, such as this one that has a lot of zeros on the file part. And that's the reason there's nothing being loaded from the original file when loading into memory. It basically says, I'm going to need this much memory. I know I will need it at some point, but just load it, whatever, and I will simply overwrite it and use it as time goes by. So after you do this, after you understand this, the bind loading part becomes pretty easy. Then we have the part on the right. Those are the operating system services, and this is done by system calls. I don't know how many of you have looked into this part. Basically, what happens is when you need something from the operating system, the CPU is going to have a special instruction. This is an example from Intel and AMD x86-64 architectures, where you have a syscall instruction. And before the syscall instruction, you pass some parameters. In this case, it's the value 1 in one of the CPU registers. There's a nice table that you can find for Linux and for any operating system that says, in this case, value number 1 is a system write command. So this would be an attempt to write to a file. It also receives other parameters because it has to know which file to write to, what it's writing to, how many bytes to write to, and stuff like that. And this is something that you have to do manually. Unicorn allows you to do that by hooking the system call function. And once you can look at the register values, you know what to do to emulate the system call in your emulator. So I said Unicorn helps us with CPU execution. What's cool about Unicorn is the fact that it's got bindings for different languages. I gave you the example of kimoon, which basically is a lot of C code. You have to go with C. Unicorn is highly easy to customize. It's got bindings for different languages. My de facto language is Python, and you can easily bind a lot of the stuff and execute and do everything in Python. Once you identify an entry point for the file, once you've done the binary loading part, you just have to specify the entry point and then do Unicorn emu start emulating, and it will start executing instructions up until the point it can no longer do that. You also have nice and easy access to writing memory, reading memory, writing registries and everything, so you can do it with just a couple of helper functions, just a couple of lines of Python to do everything you need at any point that you need. So with that knowledge, I've loaded the binary. I'm so happy. I can now start the emulation. This is an example from a piece of simple C code that just printed test. the word test. I should see this working, and it completely crashes. Not so happy then. Then I realized why. Real-life applications need more memory than they were designed. Because, for example, you have one C file that's going to, the binary will just read contents from a file, maybe write something, write a couple of numbers. It doesn't know how much data you need to write, so at some point it will need more and more memory to be able to do that. So, of course, we have system calls for that. Like I said, the operating system ensures memory management and everything. There's mmap, there's break. Each of them gets used in different contexts. And you have to also emulate these. So these are about the basic system calls that you need to be able to handle for an unpacker. But once you have memory management, you also have to do some sort of memory manager thing, similar to what the operating system does. And this is where it might get a bit tricky, because you basically have to emulate the stuff that the Linux memory allocator does behind the scenes. That's not extremely well documented, but again, you can find some hints, some examples online, and with a bit of just basic arithmetic stuff seems to go along pretty well. So, like I said, I will run you through a couple of examples. First of all, UPX. I said UPX is the go-to tool right now for packing Linux binaries. It's used a lot for like IoT malware, for stuff like that, because it's got a pretty nice and low fingerprint, so it's not very operating system intensive, doesn't use too much CPU, doesn't use too much everything. It also reduces the size of binary, and it's nice and open source. You can easily take it, reuse it, maybe even customize it, change something inside to hinder an analyst's work. I also have 3 packers that I found on GitHub, basically. Well, I dug them up from a presentation that seemed pretty cool and interesting with the stuff that they do. I decided to give those a shot, because once you are able to handle a couple of packers, you should generally be able to handle about any type of packing that malware uses. You might run into some special cases, but normally you would have, when automating large-scale stuff, most of the things will just work. And I'll show you an example of a malware sample, where not necessarily the packing part and unpacking part is interesting, but just the fact that you can gather more and more info from emulation. And if you're wondering how I chose those 3 packers, I said I found them in a presentation. It's from a presentation at RadarIcon by Unix Freaks JP, one of the people behind the Malware Must Die project, if you've ever heard about it. If not, basically, there's some people who have been tracking Linux binaries, Linux malware for a good number of years now. They know a lot of things about what attackers do and things like that, and at some point looked into how malware authors pack their malware and how you can actually get about to seeing what the executable does during your analysis. And on one of those slides, they just said, okay, so these are some cool packers I found online. And I said, okay, cool packers sounds interesting. If I can unpack a cool binary, then I should be able to unpack everything, right? So, first example is UPX, but I've decided to make things a bit harder, because UPX, like I said, just has a decompression command that you can use. And there's a simple way to bypass that. Basically, at the beginning of a binary that's been packed by UPX, there's a header. The header contains the string UPX exclamation mark. If that marker gets ruined in any way, like substituted by 4 random bytes, ABC question mark in my example, the UPX will no longer be able to uncompress it. It will give you a nicer message like this: I'm sorry, I can't unpack this because it seems to be corrupt. So that's what I did. I took a test file. In this case, it was the Linux ls binary. I packed it with UPX, and then, tested that it still worked, modified the header, again tested that it worked, and then tried emulating it. Do you think it worked? Nobody has any idea. Of course it worked, otherwise I wouldn't be here. First things first, make sure that you cannot find the original strings inside. That's a lesson I learned the hard way. So basically, if you do ls ---- help, it's going to tell you usage, whatever, it's going to tell you some stuff. I just checked that the strings no longer appear inside the binary that's been packed. After that, I emulated it, and at one point, emulation can only take you so far. Stuff will crash, and at that point, I just had Unicorn dump all the memory to separate files, and just used grep to search for the strings. And you can see the usage strings over there. So basically what happened, emulation managed to get the unpacked version into memory, and at that point, I dumped the memory and had access to the original malware contents. Well, Alice in this case, not malware. So the UPX example works. It also works with minor modifications. On to the next one. The next tool, this is one of the cool packers. It's called PackerElf. You can find it on GitHub. It's got support for 64-bit binaries, which I was interested in. And I tried using it and emulating it, and my emulator crashed. And after about 1 day of debugging, I realized why it crashed. The reason it crashed is that the packer seems to crash itself. So basically, the stuff that I would pack wouldn't even execute outside of the emulator on plain old Linux. So like I said, research goes up and down, up and down, up and down, and this was one of the downs. I gave up on this, since if you can't use it to pack and execute your malware, I don't see any point in analyzing it. So I went to the next one. The next one is called ElfPacker. This one, I needed a new target for it. It's just simple code that would print Adrian was here. Bad idea to use test as the keyword you're searching for with statically compiled binaries. Very bad idea. Why I needed a statically compiled binary was the fact that the way ElfPacker was is by creating a code cave. Just looks for a large number of null bytes inside the original file, and then is going to overwrite them and set the entry point of the binary to to one of those addresses. So it's going to start execution from a section that was originally null bytes. That's why you have to do static compilation to have a good chance of finding a lot of null bytes in memory. And with that, I did the exact same thing, emulated the binary, lo and behold, the string was in there. I was very happy until a typo brought me to this thing. So because of a typo, I saw that, oh look, I have the string in clear text inside the original file. Basically, I did not unpack anything. What's going on here? So back to the documentation part, it actually said, had I read the documentation completely, I don't think anyone does that, but it only does encryption of the text section of a binary. So one binary will probably have code sections. It might also have data sections. And static strings, like this one, will go into the data section. And ElfPacker only packs the code part, unfortunately. So in this case, you can't, if you're trying to write some malware and pack it using something like ElfPacker, I would recommend against it because it's going to leave a lot of things hanging around in clear text. So my third target of opportunity that seemed the coolest is called MidgetPack. And MidgetPack seemed interesting because instead of just doing like simple XOR instructions or stuff like that, it actually did cryptography, like good cryptography. You can see the list of algorithms there. I went with the password-based version. You can also specify a key file for decrypting on execution. I went with password-based basically because I was a bit lazy and didn't want to mess up with a separate key file. First thing first, make sure that the strings actually get encrypted. Okay, like I said, I learned that the hard way. Then went about doing the same thing, emulated the binary, dumped the memory, and the string appears in clear text. And if you might be wondering, okay, but this is cryptography. Cryptography generally moves about pretty slowly. You have a lot of CPU instructions being executed on and on and on. Some of them are pretty slow compared to others, like basic XOR. How fast does this work? Well, my first attempt needed an overnight run. Then I discovered I had actually used a nice debugging feature in Unicorn, which allows you to hook stuff onto every CPU instruction. And it was just incrementing a basic counter by one. Once I was able to figure that out and comment that line, it actually ran in about 2 to 3 seconds. That's about as fast as you can get, especially since we're dealing with cryptography stuff. If it was just one of those simple XOR packers, it moves blitz. Emulation apparently seems to have gone a far way. I don't know how many of you have used an emulator like Box or Kimo or anything before, but Unicorn is actually doing a pretty good and fast job at executing these. And on to the malware sample. With the malware sample, I didn't focus so much on the packing. Like I said, now that I know I'm able to create general packers, I would like to see how can you use this for more analysis. And the idea is system calls, again, because anything that malware needs to do is going to do via system calls. So just by hooking those, you can see poke some interesting system calls and see what happens. And this is an example from one of the many Mirai binaries that exist in the wild, which is actually opening a socket and trying to connect to 8888. You all know that IP, okay, it's the Google public DNS server, and this is a behavior that's been spotted in some of the more modern and modified Mirai phones, where they would try to connect to 8888, basically just checking if they do have an internet connection available. And if they do have an internet connection available, they say, okay, this is not a sandbox machine, I'm just going to continue executing and actually doing the malicious part now. And you can actually see this using an emulator, and you can go forth and look into more system calls, and then you can see it also binding to a socket and starting listening on a port. So just with a simple Python script that's able to handle a couple of general cases, you get to the point where I can say this binary over here does a connection check and then goes about listening on a port. It's probably a backdoor. It might be trying to host malware and spread it around for other people to use, or whatever. Most likely a backdoor, I would say. I haven't looked into it much more than that, but like I said, it's useful info. It's very useful info when you're trying to analyze a binary first and you don't have too much information, especially because of the layers of packing that get added to it. So, in conclusion, I would say that the emulation approach is worth it. People have been using it for some time, but it did have its limitations. Right now, with something as easy to use as Unicorn, you can easily do more and more advanced analysis at scale using this. The information you gather is useful. I mean, for me, it's very useful to be able to get a foothold on what's going to happen on execution. I might decide to sandbox this sample. I might decide to say, okay, this is clearly something bad. I don't care. I'm not looking into it anymore. But you can just use it for a couple, 2 or 3 seconds run can actually get you a lot of info that you can then use for more advanced analysis. It's pretty easy to customize. So everything that I presented here is just about 100 or 200 lines of Python code. That's about all it takes. After you do install a couple of package dependencies, it's like 200 lines of code. That's awesome to me. Like I said, it's fast. It's fast and it's very easy to deploy at scale because you're basically just installing a Python package wherever you want to try and do the simulation. And research is fun. It's a nice game of ups and downs and everything, but at the end, I found it to be incredibly enjoyable, worth it. And if you people are not doing any sort of research on your own now, I highly encourage you to do it because it's actually an enjoyable activity. And I think you like it, and I think more value will get added to the world that way. And that's about it for me. If you guys have any questions.
Keep in mind that for every question we take, we're also offering goodies. Yes,
and we have... Can I ask a question then?
In another speaker's presentation, sure. We have 2 microphones that we'd like to offer to people in the audience. Yes, the person over there.
Hi. Is this on?
Yeah.
Yes. The Unicorn thing is actually a framework, and we can use it, or?
Yeah, you can just download it off the internet. It's open source.
It's on GitHub, right?
Yeah, you can find it on GitHub. I think you can just do pip install Unicorn on any box. I think it's a bit more, I think I had to do some more work for Python 3 or something like that, but that's about it.
And are you using it right now for production or stuff like that, or just to identify?
We're not using it for production right now, so this is a POC. I only started some time ago. I did some work on it, but it's still in a POC phase. It's able to do quite a lot of things, more than I expected actually, but hopefully we'll be able to use it one day.
Okay, I guess we can just Google it, right, and find it?
You can Google Unicorn, yes, of course.
Thank you.
Results may vary.
Yeah.
Hello. You mentioned before the honeypots.
Yes.
Can you tell us what type of honeypots are you using to capture malware?
Well, we're using both open source stuff that you would find online, like Dionia, the regular honeypots that you can use. We also have some stuff that we developed on our own for different kinds of things. I know we use a lot of different ones. So we have like Kudania for SMB and a couple of other protocols. We have web honeypots. We have some which are targeted at custom exploits for different types of systems. So basically, when something comes about and seems to be dangerous to a lot of systems at scale, we try to create a honeypot for it. As simple as possible, just drop a Python script that binds to a port and says, okay, I'm vulnerable, exploit me.
Hi, and thank you for the presentation. So you showed us on a C compiled program on, I guess it was on an Intel CPU.
Yeah.
Does this work also on an ARM or a MIPS CPU?
So my POC right now, no. I want to expand on it. I just base myself on the fact that the people doing Linux malware right now, they supply binaries for a lot of different architectures. So they supply them for a lot of different ones. It would need to get a couple of modifications, but Unicorn is able to do that without a problem. So it supports a lot of different things. The only thing would be, like doing it on Linux is easier than doing it on Windows, I guess, because Windows binaries are a bit more convoluted to execute and everything.
Yeah, that's
But
right.
you can definitely use Unicorn for MIPS and ARM and everything like that.
Okay, thank you.
Let's take some questions from another part of the audience. Let's take it from the left. Or I guess not.
I was wondering if the time efficiency that you mentioned could be worth to be used in real-time file content analysis.
I actually don't think so. Basically, I don't know, when you right-click something, go scan this file or something, it would take kind of a long time. And if you have real-time analysis, okay, you don't have to right-click and everything, but when I double-click a binary on my system, I would expect it to just start. And I'm adding a 1 to 3 second delay over that. The thing is, what happens with antivirus products now, it's been going on for a good number of years now, they do some sort of limited sandboxes inside for analysis. So this is not, I don't think this would necessarily be efficient, for an endpoint security product, but when you do offline processing of stuff and try to do it at scale, I think it's definitely worth it.
So basically, this model should be used only for static, punctual analysis of the files.
Yeah, it's used for a system like ours, which does a lot of online processing, but well, it's more like offline processing, since we do it in the cloud with stuff that we're able to crawl and find in honeypots.
Okay, thanks.
One last question. Let's take one from the other side of the audience, please.
Hi. My question would be related to the fact that, okay, Unicorn Metasploit, any kind of free framework, it's adding a little specific pattern to the files, so also the signatures. So you basically run those malware instructions in memory. If you plan in the future to have a research on how to do it with files written on the hard drive, except the obvious version of encrypting it, if you plan to do some research on that.
Well, not necessarily, because like I said, the stuff we work with most of the time is just stuff that we get and we send to our backend processing system. So basically, when we get something in a honeypot, we know it's likely, who is going to upload Windows Calculator when doing an RCE against a honeypot, right? It's most likely malware. We just try to find if it's malware, if it's interesting, how it behaves and stuff like that. Static analysis, we also do dynamic, and sometimes, like in this case, you need something that moves well in between.
All right. Thank you, Adrian, for this awesome presentation.
Thank you.